fast charge phase, which for our battery is 125 amps. So it charges that maximum current until it detects the battery approaching its peak capacity. Once that happens, it'll move into trickle charge phase, which continually tops off the battery without overcharging it so that it might overheat or rupture. If there are any errors in this process, it will signal it by alternate flashing. The system that it uses to detect the peak charge is called a negative delta V cutoff system. This is based on an inherent electrical characteristic of nickel cadmium and nickel metal hydride batteries, that as it nears full capacity, the internal pressure will rise, internal resistance will decrease, and so the terminal voltage will begin to peak. The peak for these kinds of batteries is about 20 millivolts per cell. So we have a 10-cell battery. And so we did tests, and this is one of the tests we did for a nickel cadmium battery, and we found that just as it reached that cutoff of 20 millivolts per cell, it would switch immediately into the trickle charge phase. We chose nickel cadmium technology because it had a relatively low self-discharge rate. This was significant because we would only be charging for 1 hour a day. 2 hours it would be spending, on average, powering the LED lamp, and the other 21 hours, nothing. And so it's a significant portion of this time not being charged. We need to reduce the loss as much as possible. We found that over 24 hours, the loss was negligible. And yet we were still able to power the LED lamp. Additionally, we chose a high milliamp hour rating because although this increases the energy capacity to something that far exceeds what we need on a daily or weekly basis, it allows us to have a higher standard charging rate, which is significant because we need to charge the battery as fast as possible within that 1 hour, because we only get that 1 hour a day. Mike will talk to you about future implementation.
So as was mentioned before, if we want to implement this in the future, we need to change the blade configuration of the turbine. Instead of having one that moves air, we need one specifically designed for water. We can consider an impulse or a reactionary turbine. The reaction turbine is fully submerged or encased to hold the pressure. Impulse turbine, you can shoot a jet of water straight at the blades and then rotate. Water pressure considerations, we need to make sure that the seals aren't broken by a high pressure, and to make sure that the pressure delivered to the household is enough to use daily household devices. Finally, the flow control system for the lower cache. You need to control exactly when and how much water comes into the lower cache from the upper cache. Unfortunately, we couldn't do this on a large scale, so this is just a conceptual idea as far as we're concerned. At this time, we'd like to acknowledge Professor Weisstrom and Wayne and the senior design faculty. And at this time, we'll take any questions.
Thank you, team. Team, I'd like to begin with a question. So I believe Victor said that you were planning on charging this for an hour. Do you know what, I don't remember the specs, whether it was a 2-inch or 2.5-inch. How much water would you actually be using?
400 gallons.
400 gallons per day.
That's given the 6.7 flow rate. But because it was easy, in order to design the turbine, it makes more sense to assume a flow rate. So we figured we could drain 400 gallons at that rate. It's reasonable given the size of the pipe and everything. And if we can control it to that, then you can I mean, we didn't design the turbine around it, but that would be kind of the idea that you want to go with. If you were, I would suggest getting a company to actually design the turbine. So, where you think like for that sort of.
Other questions from our audience?
I'm curious to follow up on that. Can you talk about what 400 gallons means in human terms? How many showers or toilet flushes?
Basically, I mean, 400 gallons was decided on because it's the daily average use of a household. So You know what I mean? I mean, you can never, it could, I mean, every day it's going to change, but we wanted to model the system around a certain amount of water use, because, you know, what's the average use? So that's where we found that.
And
I don't know exactly how many showers and 40 gallons per shower.
I don't shower at all.
A flush is 2 gallons.
Yeah, yeah.
That's a convention.
But it's also based on a 4-person family. So
And
suppose,
what's the energy we're talking about in a day?
well, I mean, depending on the efficiency of the system, up to, I think the maximum is 62 watts. 62 watts
60.
for that one.
Yeah, I have a question on the battery charger. You're using 7.2 volt NiCad batteries or something like that, as I recall.
Well, in the chart, that was just the data from a test that we used with a 7.2 volt nickel cadmium battery. We're actually using a 12 volt battery rated at 2600 milliampere hour.
Okay, so but you have a 12 volt NiCad battery. Can you talk about why you developed your own battery charging circuit? Seems to be commercially available NiCad battery charging circuits.
All the available commercial nickel cadmium batteries chargers that we found were again based on a constant power supply. They were designed so that you can just plug it into an outlet, and we didn't have the luxury of having an outlet out there. I think that was part of the issue that we're trying to deal with the heavy power system. And a lot of them were just straight chargers that we could have built with a few resistors and a voltage regulator. It wouldn't have any capability to prevent that overcharge that we needed. Since we want to maximize the battery life and to maximize the life of the system,